organizations often talk of storing their data in a data lake, it's become a catchphrase for any big data repository, when in reality there are different maturity levels for a data lake. Most organizations start off with what's referred to as data puddles. These are single-purpose data lakes that are used for a very specific purpose in a limited context, such as a single project. The next maturity step is data ponds, which are collections of data puddles in a project. Perhaps a project contains several teams, each with their own data puddle for managing data related to their aspect of the project. Data lakes move beyond the idea of data custom to a specific project or purpose to self-service data that can be sourced by anyone who has a need for it. Data in a data lake might be generated to address expected future uses, such as results of predictive data analysis. And a data ocean is a data lake taken to the enterprise level. A data ocean is a source for self-service data, and the enterprise uses the data for their data-driven decision-making strategies. So first, let's talk about data puddles. Data puddles contain data for a specific use. An example is when a developer uses a local relational database as a sandbox for testing the application they're building. In the context of cloud technology, teams have turned to building data puddles using big data technology because this opens up the ability to perform analytics that are just not possible with smaller data sets. Additionally, the tools for performing such analytics, such as machine learning or AI, are built around big data sources in the cloud. Another common use for data puddles is data storage that facilitates data pipelines, such as extract, transform, load, ETL pipelines. In this case, the data puddle's specific use is to temporarily store data as it moves along a pipeline. And usually there's no other use for the data, and no other process accesses the data other than the pipeline itself. The common theme with data puddles is that they're a collection of data that's dedicated as a specific part of a process or use case. Data ponds are a collection of data puddles. One common use for data ponds is when companies take the leap from dedicated on-premises data warehouse to the cloud. They often take the data puddles, which exist in their on-premises data warehouse, and simply move them to the cloud using big data cloud technology. The idea being that once the data has been ported to the cloud, the on-prem data warehouse can be shut down. There are a few considerations that this brings up. First, on-prem data warehouses are often fine-tuned to be performant for given use cases. Performance is highly predictable, sometimes close to real-time. Big data warehouse technology, on the other hand, is far less use case specific, and is not generally designed for real-time performance. Instead, a data pond may be sharing cloud resources, and so performance becomes far less predictable. Cloud solutions are not usually geared toward real-time performance for this very reason. But legacy on-prem solutions might not be designed to work with the possible unpredictability of cloud big data performance. When you move an on-prem data storage solution to a data pond in the cloud, you move its inefficiencies along with it. While cloud big data solutions rely heavily on agility through automated processes, processes might still be largely manual in the legacy data solution, and they'll continue to be manual and require manual attention even in the cloud. And it's important to note that data puddles, by definition, have limited access because they're designed for a specific use or process and are therefore only accessible by a single group of people or a specific process. To be truly effective, data lake data needs to be accessible to everyone. A company's data solution becomes more of a true cloud solution when it matures from data ponds to a data lake. A data lake is not focused on internal processes, but instead is focused on business strategies. To move to a data lake approach requires buy-in from the entire organization, right up to the corporate level, because it's a transformation from the project-focused view to a platform for self-service data that serves users in business analysis of the data. Pick a platform carefully because it will be the backbone of your data strategy. So it must be future-proof, it must be affordable now and in the future, it must be appropriately scalable, and it must support all data formats that you're planning to use now and in the future. Also, a data lake must support not just the data required today, but it must also anticipate what might be required for analysis in the future. Because when you decide to perform historical analysis, you'll have to have already been collecting that data for some time. You must also give careful consideration to how data lake users are going to interface with the system. For instance, is the nature of your business that the data lake will mostly be accessed by individual data scientists, or will there be various automated services interacting with it? These questions and others will help you determine the interface for your data lake. Ideally, data ponds grow to become data lakes, and eventually, as they're taken organization-wide, data oceans. Unfortunately, many data ponds never mature into functional data lakes. Instead, they go largely unused, turning into what's called the data swamps. So what makes data ponds become unusable data swamps instead of data lakes that are the backbone of a data-driven organization? Well, here are a few reasons. The data is not made easy to access. Ease of data access is of utmost importance. Otherwise, people are not going to use the data. Governance can be strict and can restrict access to the data, especially if the data is sensitive or regulated in some fashion. In these cases, the data cannot be accessed by everyone, and perhaps this type of data should not be a part of your data lake. You may hear data lake proponents tell you that it's best in the beginning to just collect all the things into the data lake and not worry at first whether you're going to need them or even what format they're in. This can be true to a point. Collecting a lot of data at first, then later paring it down and making it accessible in an effective manner can work. But simply collecting data without a long-term plan can lead to data that's unusable because it's perhaps in an unknown format or people don't even know it's there because it's not documented anywhere. And finally, for a data pond to flourish into a data lake, the data needs to be accessible. Accessibility can be hampered by the format of the data, for instance, if it's encrypted. In this video, we're going to look at temporal database tables. Temporal tables store both current data in a current table and historical data in a history table. They're also sometimes called system version tables because the database manages the versioning of records for you. Throughout this video, we're going to be looking at temporal or system version tables as they're implemented by SQL Server. So what are some of the use cases for temporal tables? Well, the use cases all call for maintaining change history of the records and being able to query those changes with time as a variable. Data forensics is one, where the history of changes is queried to look for patterns that match a forensic investigation. Data reconstruction is another. For example, an application that shows what values were at a specific time in the past. Looking at changes over time can show important data trends. For example, a database might store daily stock market values in a temporal table, so trends can be shown for a stock over time. Slowly changing dimensions are fields in the database that rarely, if ever, change. An example might be the last name of a user stored in the database. The last name may change, but not very often. A temporal database can capture the history of these slow changes and allow for functions like rolling back to the previous name. And temporal tables are useful if an application needs to be able to roll back changes to fields to a specific time in the past. Say someone enters the wrong data and wants to undo it. Here's the SQL statement for creating a temporal table. Note that like most tables, it has a primary key, student ID, and regular fields such as first name, last name, date of birth, etc. Then there are the valid from and valid to fields, and these are temporal fields. Note the format. They're of the type datetime2, and they're defined as generated always as row start and generated always as row end, respectively. These are called period columns and are managed by the system. The names valid from and valid to are actually not of practical importance. They could just as easily be called start time and end time. What is important is how they're specified. Then the statement ends with a with statement that specifies system_versioning as on. This is what tells the system to manage the defined period columns, and that's what makes this a temporal table. And the history_table statement defines the name of the history table to be student history. If this is omitted, the system will create its own history table with a unique name. So now let's look at what happens with the current and historical tables during standard table operations. First, when a new record is inserted into the current table, its row start period column is set to the current transaction date time, and its row end period column is set to the maximum datetime value of December 31st, 9999. During a record delete, the deleted row is copied to the history table. The row end column for the history table record is set to the current transaction datetime. Then the row is deleted in the current table. If a record is updated, the row in the current table is copied to the history table, and that record's row end column is set to the current transaction datetime. Then the current table record is updated with new values, and its row start column is set to the current transaction datetime. And finally, during a merge, the insert, update, and delete operation behaviors already mentioned are in play, since a merge is basically some combination of those actions. Now, the real power of temporal tables is being able to query the data across time. There are several options for doing this. The as of option allows you to specify a single date time and get the results as they would have appeared at that time in the past. You can also query with from and to statements, which allow you to specify a start and end date time and get all records that were valid in between those date times. This includes records that might have become active before the start date time or become inactive after the end date time, as long as they were valid at some point in between the given start and end date times. Edge cases, that is, records that became inactive right on the start date time or became active right on the end date time, are not included. Using the between and combination is similar to from to, only it includes the edge case of records that became active right on the end date time. Contained in returns all records that became both active and inactive within the date time range. This includes edge cases of records that became active right on the start date time or inactive right on the end date time. And finally, the all option returns all records from the current and history tables that correspond to the queried data. Here is an example of using between and to query a student table. Note the for system_time before the between and option. This comes before all the expressions we looked at in the previous slide and specifies that what follows is a system time expression. In this case, all records with student ID of 1000 from both the current and history tables will be returned as long as their period columns state that their time range of validity falls between January 1st, 2020 and January 1st, 2021. Obviously, it'll include any records that have start and end period columns that both fall within that range, but also period column values that are only partially within that range, such as a record that became valid on November of 2019 and was invalidated on January 2nd of 2020. That would count because its effective range overlaps the system time expression range by a few days. Because it's a between and, if there's a record that only became valid exactly on January 1st, 2021 at midnight, that record would be included. In this video, I'm going to show you how to create a temporal table in SQL database in Azure. Now, temporal tables store records like a normal table, only when records are updated, the previous history of the records are stored in a separate history table. This way, temporal queries can be performed, which query data as it was in the past. This can be useful when you need to see the state of records in a specific time in the past, or when you want to query for trends over time. So here I am in Azure Portal, and the first thing I'm going to do is go to my SQL database instance. So in order to do this, you need a SQL database instance set up. And the first thing I'm going to do is check my firewall, because you need the firewall set up in order to correctly use the query editor. So if it doesn't already exist in your rule list, make sure you hit Add Client IP at the top and click Save. Now I've already done this. You can see my client IP address in the middle of the screen, and you can see that it's in my rule list. So as long as it's there, then it should work. It's important to note that IP address changes occasionally. So in order to keep using it, you may have to come back and reset the firewall. So going back to my SQL database, on the left I'm going to click Query Editor. And I'm going to log in using the login and password that I used to set up my SQL database. Okay, so here we are in the Query Editor. If I expand tables on the left, you'll see that I have no tables set up. So what I'm going to do is create a temporal table, and then we'll talk about the query. So here's the query for the temporal table. So it looks a lot like a regular table. Create table, and my table is called people. And I have fields just like a regular table. I have a field called people ID, which is my primary key. I have a field called name, which is a character array, so it's a string. On line 5, I have age, which is an integer. And then the next 3 fields have to do with the temporal part of the temporal table. To have a temporal table, you need to have a sys start time, just like on line 6, and it's a date time too, and it's a generated field, and so it looks like generated always as row start, not null. And then on line 7, we have sys end time, which is also a date time too, generated always as row end, not null. So what these fields do is they keep a record of the effective start and end time of a given record. And then on line 8, we have period for system underscore time, and in round brackets, sys start time, sys end time. So for the temporal behavior of the table, it sets up which fields are the start and end times for the system. On line 10, we have with, and in round brackets, system underscore versioning equals on. So you have to set this in order for it to be a temporal table. Now, we'll hit run on this, and we'll see what happens. Okay, so that's succeeded. So if I hit refresh on the left, and I open up tables, now you'll see we actually have 2 tables here. We have our dbo.people, which is our people table we just created. And we also have MSSQL underscore temporal history for underscore and a big number. This is the system-generated history table for the people table. Now, what we could have done is we could have given the history table a name that we recognize, but I just let it default, so it just creates a default name. Now, if I open up the fields of people, so we have our primary key, people ID, name and age, which is our fields, and we have sys start time and sys end time, which keep track of the temporal details of our records. If I open up the history table, you'll see that it has exactly the same field, so it's a duplicate field-wise to the regular table. So what it's going to do is, in the people table, it's going to store the most recent records, and when you update records, history of what the records used to hold will be stored in this historical table. So why don't we go ahead and add some records and see how these tables behave. So in our query window, I'm going to insert some people. Insert people ID, name and age. Values are going to be Fred Flintstone, and he's 43 years old. Betty Rubble, she's 32, and Pebbles Flintstone is 3. And they all have a unique people ID. So I'm going to run that. Okay, so that succeeded. So now what I'm going to do is I'm going to query people, select all of the records from people, and you can see our 3 people at the bottom, Fred, Betty, and Pebbles. Now let's take a look at the history table. I'm just going to right click and choose select the top 1000. And you see that the history table is empty. So that means there's no history yet all of the records are recent records. They're the most recent records in the people table. Now let's do a query where we modify one of the records in the people table. So I'm going to update people, and I'm going to set Betty Rubble's age to 41. Let's say we made a mistake, and Betty Rubble's age should be 41. Let me run that, and that's successful. Now let's take a look at what's in our tables now. So I'm just going to run the query to take a look at all the records in the people table. Okay, and you see there's still just 3 records, one for each, and you'll notice that Betty Rubble is now age 41. So that's our most recent record. Also, let's take a look at the sys start time and sys end time. Notice that the sys start time for Betty Rubble, it says 1805. This is in UTC time. So this is the time that Betty Rubble was modified. It was today, which happens to be February 18th, and it was at UTC 6:05 p.m. Now, if you take a look at the sys end time, notice that it has a year of 9999. What that signifies is that this record is valid. Right now, it's the most recent record, so it's valid to essentially to the end of time, or until the record is changed again. They're all like that because they're all the most recent record. Now let me take a look at the historical table. Now the historical table has a record in it, and it's Betty Rubble when she was age 32. So this is a copy of the record with the old values. The start time is 8:03:46, and the end time is 8:05:04. So that's how long this record is valid for. It was created at 8:03:46 when she was marked as age 32, and when we changed her age, it stopped being the valid record, so it stopped at 18:05:04. And if we take a look at the original table, that is exactly the time in which the new record was created and became valid. So every time a record is updated, the previous record that it held is going to be copied to the history table, and we'll keep a history of all the changes. So you'll always be able to reference the record the way it was in the past. Now let's take a look at the queries that allow you to actually query it. So the first one I'm going to do here is select star from people for system time, and I'm going to put a system time back in the past, January 1st, 2020. And let's see what that does. And I get no records. And the reason I get no records is because January 1st, 2020, this table didn't even exist. So there were no records in it. So that's valid. That's the people that were in the table at the time. So if I look at the history table, I see that Betty Rubble's age of 32 is valid from 1803 to somewhere around 1805. So I'm going to copy that, and I'm going to go to the other query and change the query that selects all the records from people. And I have to give it hours, minutes, and seconds. But I'm going to give it a time of 1804, which I know is in between there, so it should be valid. So let's run that. So now we get 3 records back. We get Fred and we get Pebbles because they haven't changed. And we get Betty Rubble, and you notice Betty Rubble is age 32. So what we get is we get the table as it would have been seen at 6:04 p.m. UTC time on February 18th. So sometime between the time of 6:04 p.m. and 6:06 p.m., I changed the age of Betty Rubble to be 41. So if I change the query to say system time as of 6:07 p.m. and I run it, you see that I now get the table back and Betty Rubble is now 41. So this is how we can query the table and see its contents at a specific point in time. Now let's say we want to compare records from different points in time. Well, the way you can do that is with a different query, and I'll just bring that up here. This is a between and, so for system underscore time between the start date and the end date. So for instance, I'll just use the days. So I'll say between the 15th of February and the 19th of February. That should capture all of our records because all of our records reside on the 18th of February. So if I run that, and you can see I didn't take the first select, we'll have run the second one. You see that I have 4 records now. I have 2 records for Betty Rubble, one when she was 32 and one when she was 41. And if I want to do some comparisons of this, I can query the system start time and end time on those records to see when they occurred. So this is a way that you can do a temporal query to compare records according to what they were at certain times. So in conclusion, temporal tables are great for data for which you need to maintain change history. The system automatically manages the history for you, so you can perform temporal queries on it. In this video, we're going to look at slow-changing dimensions. These are data dimensions that rarely, if ever, change. As an example, imagine you have a system that ingests data from a physical refrigeration unit. Now assume the unit is on a truck, and the truck moves from one city to another every few months. The temperature being read from the refrigeration unit may not be slow changing. It may be updated every minute, for example. But the location of the unit may be considered slow changing, since it only changes location every few months. The temperature is what is called time series data. Each value is time-stamped, so you can see a trend over time. The location, on the other hand, is not time series data, but you may want to keep track of historical values when it changes, if nothing more than to accurately represent the location on a past report when it's issued. Now, there are several methods for managing slowly changing dimensions, depending on your requirements. The first, or type 0, is the passive method. This means that the value is written once and never changes. For example, a person's birth date will never change, so it can be written once in the database and that's it. Another option, type 1, is simply to overwrite the old values with the new ones in the database, and not to bother recording historically what the previous values were. This is a very simple approach, and if you have no need for the historical values, this may suffice. In my experience, however, many of the systems I've worked on featured regeneration of historical reports. For example, you want a report of conditions of a well field last month, and this report must look exactly as it did when it was generated on the day in question. The system cannot necessarily accurately regenerate such a report if it didn't record the previous values of slow-changing dimensions. For example, what if a well's name is changed? Type 2 is to create new records for each change and to keep special columns for managing historical records. A common method is keeping a start and end time for the valid time range of the record. This way, a system can regenerate a historical report by looking back on what the slow-changing dimension values were in the past. Type 3 is to add a column so the current and previous values of a dimension can be stored in the record. This allows a one-step look back to see the previous value. Type 4 involves a complete historical table, where historical records are kept in the historical table, separate from current records in a current table. And finally, type 6 is a combined approach that uses different combinations of the previous types as requirements demand. Now note that there's no type 5. Type 5 is actually a variant of type 4, but instead of creating a whole new record per change, only a subset of the columns are recreated. So in reality, type 5 is a special case of type 4 and rarely mentioned. It's worth mentioning that the majority of situations will be handled by types 1, 2, and 3. The other types are used in special cases as requirements dictate. So let's look at some examples. First, type 1. In this case, the slowly changing dimensions are last name, first name, and major. Note that the original record and updated record are identical, except that the major value has been changed. This records the current value only, and all historical values of major are lost. Next is type 2. This is when each change is represented by a new record, and there are special fields for managing different versions of the record. Here we have 2 examples. In the first one, there are two records representing student ID 123456. The major values have changed. There's a version column that keeps track of the version of the record. Version 0 would be the original record, and every time the record is changed, a new record is created with the change, and the version number is advanced. This is useful if actual date ranges are not important, and instead you want to see changes by version alone. In the second example, again there are two records representing different versions of the student ID 123456, and they have different major values. Start date and end date columns represent the effective valid range of each record. So the current record is ID 1001, which became valid January 1st, 2021. Its end date is null, which represents an open end date since it's the current record. The record with ID 1000 became valid on January 1st, 2020, and then became invalid on January 1st, 2021, when the record ID 1001 was created. Next is type 3. This is when two separate columns are used to store the current value and previous value of a slow-changing dimension. Note that we have major and new major. When the major dimension is changed, the current major value will be copied to the new major column, and the major column will be overwritten with the updated value. New records will have an empty new major field. The limitation here is that only the very last historical value is stored, and all others are lost. With type 4, there are two tables: a student table, which holds the currently active records, and the student history table, which holds the historical records. In this case, when a new student is added, a record is added to the student table. Then, when the record is changed, a copy of the existing student record is copied to the student history table, and a created date is added. Then the student record is updated. In this way, all history of the slowly changing dimensions is maintained in the student history table. And finally, we have type 6, which is a combination of previous types. In this example, there's one student table. When a new student record is added, it's added to the table with a start date of the transaction date time and an end date which has the year 9999 and represents an open end date. Then when the student record is changed, as shown in the bottom table, the existing record's end date is set to the transaction date, and a new record is added with the start date of the transaction date and again the year 9999 to represent an open end date. This is in line with type 2. Additionally, in this example, the major field has an additional field called hist major, which stores the previous values of major at the time of the change. And this is in line with type 3. By combining these approaches, one can query for historical ranges and also quickly retrieve the previous value of major, which may serve some requirement of the table. In this video, I'm going to demonstrate using a data flow in Azure Data Factory to implement slow-changing dimensions. Now, slow-changing dimensions are values in a database that are expected to change infrequently. So an example might be a person's last name in a database of a doctor's patients. People's last names don't change very often, but they can change occasionally. So when implementing slow-changing dimensions, you need to consider whether you're interested in maintaining a history of the changes. So in this demo, we're not going to maintain the history, but instead we'll replace the values of our slow-changing dimensions and then simply record when it was updated. So the first thing I'm going to show you here is in Azure. I have my SQL database instance open up here, and I'm on Query Editor. And I have a couple of tables set up. I just want to show you on the left here. I have a table called widget_dim_stg. So I'm going to model a very simple object called a widget for this demo. And this is a staging table, hence the STG, and DIM stands for dimensions. So you see the fields here are a widget ID, which is a primary key, a name of the widget, and a cost of the widget. So these are both good examples of dimensions that don't change very often. You're not going to change a widget's name or its cost very often. So I have put some data in this staging table, and I'm going to show you how you create a data flow that will manage those dimensions in a target table. And we have the target table here, widget underscore dim underscore 1. You'll see that it also has a widget ID, a name, and a cost. It also has some additional fields that help manage the changes. So it has a widget key, and that's the primary key. So when you're managing the history of dimensions in a separate destination table, you're going to want a separate primary key to represent each record in there, separate from the primary key from the source, which is widget ID. We also have added date. So this will give us the date of when the record was added, and updated date, which is the date of the latest update of any of the values. So I also want to show you what's in the staging table. So I've created a select statement here, and I'm just going to run it on the right-hand side. And you will see that at the bottom here, I have 3 records. The names of my widgets are test1, test2, test3. Each of them has a cost, and each of them has a widget ID, 1, 2, 3. So we'll be looking at that data as we step through our data flow. So now I'm going to go to Data Factory. I have it open in a separate tab. And in Data Factory, I am currently on Author. And I'm going to show you what I have set up here. First of all, I have some data sets, and this maps to those tables. So if I open up widget dim STG, you'll see that it maps to the widget dim STG table. If I open up widget dim 1, you'll see that I have a map to the widget dim 1 table. The next thing is the data flow itself. So down under data flows, the one we're going to be looking at is slowly changing dims 1. So if I open that up, you'll see a data flow here on the right-hand side. And if you wanted to create a new data flow, you would simply go to data flows on the left, click the ellipsis, and choose new data flow. And you could create your own data flow like this. It has different blocks, logic blocks you can use. And there are 2 paths here left to right because there's 2 different logical paths to take. The first one is for updating records, and the second one is for inserting records. So if a record is being changed that already exists in the destination, then it'll be an update. And if the record does not exist in the destination yet, it will be an insert. And that's why we have the 2. So I'm going to step you through these. Let's start with the update. So if I go to the first block on the left, it's called staging. And if I click it and you look at the settings, it basically connects to my staging table. That's my data set. And if I go to data preview, also another thing that will help with these data flows is a data flow debug option, which is at the top here. So turn that on and you'll be able to debug these by looking at the preview data and other debug tools. So I'm going to click on refresh here under data preview, and you see my records from the staging table. So we have our 3 records. So that's coming in from the input. Now let's go to the next block. The next block is called Get Update Records. And what this is going to do is it's going to find the records that need to be updated. Now the way it knows which records need to be updated is it does an exists. This is an exists block. And it finds records in the destination that have the same widget ID as what's coming from staging. That means that they're records that already exist in the destination, so they're going to have to be updated. So if I look at the data preview for this step, I should see only the records that need to be updated. So you see that there's no output data, and that's because there's no records to update. So if I go to the next block, this is called Add Destination Fields. And what this does is it will add the destination and the staging fields all together. And the reason we need to do that is because, as you recall, the destination table has some extra fields. It had the added date and the updated date and the widget key. So that's what this does. If I go to inspect, you'll see that this has the widget key and the added date and the updated date included. Now the next step is derive update columns. This is where we set the columns that we want to set for the update record. And what we want to set is the updated date value. So here's updated underscore date, and we set it to the current UTC date. So this next step is just a step that's required for updates. So we'll just step over that one. And the final step is to update the destination table. So here you can see that it's going to bring in the widget key, the widget ID, the name, the cost, the added date, and the updated date. So that's the update logic. Again, it brings in all the records. It finds the ones that need to be updated. It sets the updated date, and then it writes it to the destination. Now, what about the ones that need to be inserted? So that's the next row from left to right. So again, that brings in all of the staging records. And if we go to the next block, it says get insert records. So in this case, instead of an exists like we did to find the update records, it does a doesn't exist. It's looking for records that do not have a widget ID in the source or the staging that matches the destination. That means this is a brand new record. It's not in the destination yet. So if I go to data preview and I hit refresh, I see that all the records show up because they all need to be inserted. Now if I go to the next block, it's add max widget key. Now what this does is it gets the max surrogate key. And what this is the maximum widget key in the destination. Because remember that for inserting, we need to create a widget key, and it needs to be unique. So what I do is I get the largest widget key value that exists in the destination, and then I'm going to add to it in order to create unique keys. Now there's a special input at the bottom here called max surrogate key, and it's the one that gets the key from the widget table. So you can see here it's got a query under source options, and it's getting the maximum widget key value from widget dim1, which is our destination. And that's what this add max widget key is referencing. So you see it's referencing the max surrogate key. It's doing a custom cross join, and all that does is it brings in that field. So you're going to get the same data, but it's going to have the max widget key as a field on every record. So if we go to data preview and I hit refresh, you'll see what I mean. Okay, so here's our 3 records, and you notice max surrogate, it defaults to 1 because there are no records in the table yet. So the largest surrogate or key that we're going to use is going to be 1. Now if we go to the next block, add surrogate key root, what this step does is it creates another field which basically numerically adds to the field, so it'll go 1, 2, 3, 4, 5, and we want that field to add to the maximum surrogate key we just got in order to create our client keys. And this will become apparent when I hit data preview. So now we have our records back, and we still have max surrogate, which is all of them say 1. That's our largest existing key. And then we have surrogate key root just created in this step, and it goes 1, 2, 3. So the way we're going to create a unique client key is we're going to take this maximum client key and we're going to add the key root to it. So this one will be 1 plus 1 is 2, this one will be 3, this one will be 4. You see how that works, because if the maximum client key in the table currently was 5, then these records would then be 6, 7, and 8. So they're always unique and they don't exist in the table. Now the next block is to derive our insert columns. Now it automatically brings in all the columns that we've created here. If I look at inspector, you can see all the columns that are going to come in. So in derived column settings, I just have to add the ones that I either want to add a column or I want to change it. So I added widget underscore key, and I created it as the addition of max surrogate and surrogate key root. And then I set the added date field to be the current date in UTC. So if we go to data preview and hit refresh, okay, so we have our max surrogate record, we have our surrogate key root record, and we use those two to derive the widget key. As you can see, it's 2, 3, 4. It's these two fields added together. And the added date is set as today's date. So these would be the 3 records that go into the table. And we're going to run that in a little bit. So that's all there is to this data flow. It either updates or inserts records. So let's run that and see how it works. Now on the left, I'm going to open up pipelines. And I have a pipeline set up called slowly changing DIMS 1. And if I open that, all I did to create this was I just dragged the data flow from the left over into this, and it creates a step in a pipeline. Once you have it as a step in a pipeline, you can then run it by using a trigger. So at the top, I'm going to click Add Trigger, and I'm going to hit Trigger Now, and this is actually going to run it. Pipeline run, I click OK. So this is running that pipeline, and we'll be able to see the results. Now this often takes about 5 minutes, so I'm just going to pause and come back when it's done. So the pipeline run was successful, so now we're going to take a look at the database. So I'm going to go back to my SQL database, and now let's take a look at what is in the dim1 table, widget_dim_1. That's our destination. And you can see that we have the records in here. There's 3 records. So those are the 3 records. They have a widget key, which you can see it starts at 2 and it goes 2, 3, 4. And it has all the data, and the added date is the current date. I don't have the time because slow changing dimensions usually don't change twice in a day. You could have a date time there as well if you wanted to keep track of that. And there's no updated date because none of these records have ever been updated. Now what we're going to do next is we're going to run that again, but this time we're going to force an update and see what the records look like. So I'm going to run another query here. It's going to delete what's in the staging table and then add 2 records. The first one has a widget ID of 2, which already exists. It's this record down here, test2, and I'm going to change the name to test2 updated, and I'm going to change its cost to $14.32, or $14.32. Then we add a new record that doesn't exist. It has a widget ID of 4, which doesn't exist yet. Test 4, and it's $20.50. So this one should be an update on line 6, and on line 7 should be an insert. So I'll run that. So let's just go to Data Factory, and what we're going to do is we're going to rerun the pipeline and see what it does to our records. So I'm going to go to slowly changing DIMS 1, and I'm going to trigger it again. Trigger now, hit OK, and we'll let that run. Okay, so that's completed. So let's go to the database and see what's happened. So I'm going to select all of the data from our widget dim1 destination. So now you see that what we have is we have the record that was inserted is widget ID 4, and there it is, test 4, and widget ID 2 was updated. So you see it has a new updated name and the updated cost, and the updated date has been set. Now it's the same day as the added date because we've added it and updated it on the same day. But if it was tomorrow, then the updated date would be tomorrow. So what this does is it allows you to query this data later, and it allows you to query the most recent one because the most recent record will have an empty updated date. And you can also see when records were updated. So in conclusion, this implementation demonstrates one way to ingest slow changing dimensions and store them without the need to maintain a history of their previous values. In this video, I'm going to demonstrate using a data flow in Azure Data Factory to implement slow changing dimensions. Now, slow changing dimensions are values in a database that are expected to change infrequently. In this demo, we're going to maintain the history of the slow changing dimensions, so previous values can be queried. So I'm in a SQL database instance here in Azure, and I have some tables set up, which I'll introduce you to first. And these are the tables that we're going to use as source and destination tables for our data flow. The source table is a staging table called widget dim stg. So we're going to be modeling a very simple object called a widget. And you can see the fields here are widget ID, that's the primary key, name of the widget, and cost of the widget. So both of these would be examples of slow changing dimensions, because you don't change a widget's name very often, and you probably wouldn't change its cost very often. Our destination table is widget_dim_2. It has a slightly different set of fields. It has the same fields in it as widget dim staging with widget ID, name, and cost, but it also has some additional fields that are used for managing these dimensions. So it has widget key. This unique key is required because you can have more than one record for the same widget. So you can't use widget ID as a primary key. You need a new one. So widget key is the primary key. And we have start date and end date. That signifies the effective date range of the dimension values. So if, for instance, this widget cost $1.50 between February 1st and February 10th, then that would be the start and end dates. And maybe on February 10th, the price went up to $3. So we have an active flag, and the reason we have an active flag is, again, a single widget can have more than one record in this table. So we need to identify which record is the most recent record, which represents the most recent values for this widget. So that will be the only record that will have the active flag set. So let's go to Data Factory. I have this open in a separate tab. And in Data Factory, I have my data flow set up. So let me show you the pieces to this. First of all, under Data Sets, I have connections to those tables. So I will just jump into Manage for a second here on the left. In Manage, under Link Services, I have a link to that SQL database I just showed you. If I go back to Author on the left, under Data Sets, I have my widget dim STG, and that's linked to the widget dim STG table. And I have widget dim 2, and that's the widget dim 2 table. So we have those mapped. Now if I go to the data flows on the left and I go under slowly changing dims 2, so here's my data flow, and the data flow is in two parts. There's one part for inserting records, and the second part is for updating records. Now the reason you need to insert and update, first of all, any change will involve an insert, because if the widget already exists in the destination, you're still going to insert a new record, because every change is going to be represented by a new record. You also need to update records because you need to mark the new record as active, and you need to mark any older records for the same widget as inactive. You also have to set the start dates and the end dates. So let's take a look at these one at a time. We'll start with the insert destination. So this is the insert row at the top here from left to right. First of all, it gets the data from the staging table. So if I click on this first block here, you see under source settings, the data set is the staging table. And if I go to data preview and I hit refresh, I can see the data that it's bringing in. While that's happening, by the way, up at the top bar here, you should have data flow debug turned on, because what that will do is that'll allow you to use these debug tools such as data preview. So you can see that I have some records in my staging table. So I should mention that I have set up this staging table so that I have an update ready to happen and an insert ready to happen. I have widget ID 1, which is going to change the name of that widget to this has been updated, and it's going to change its cost. And I have widget ID 4, and this is a brand new widget. Now just to put that into context, I'll quickly jump back to the tables in my SQL database. And if I take a look at what's in my destination table, you'll see that I've already populated it with one record. It's widget ID 1. I gave it a widget key of 15. You'll see why in a bit. I didn't want that to be 1. I wanted it to be some recognizable number. So widget key is 15. Widget ID is 1. It currently has a name of existing widget and its cost is $1.15. We can see that its active flag is true because it is an active current record. It has no end date because its effective end date is to the end of time until there's a new value. And the start date is February 15th. So if I go back to Data Factory, this widget ID 1 that we have listed from in staging is going to update that record. And 4 will be a brand new record. Now if I go to the next step here, add max surrogate key. Now what this is doing is this is the first step in preparation for creating that widget key. So remember, the destination has a widget key as a primary key that does not exist in staging. It's a unique key in the destination. Now the way I manage that is if I go down to the bottom of my data flow here, there's an input that's called max surrogate. And I'm calling that the surrogate key. In the table, it's called widget key. So max surrogate is tied to the destination table, widget dim2. And if I look at source options, what it's doing is it's selecting the largest widget key out of widget dim2. So I get that, and if I go back to the step I was just at under insert destination, add max surrogate key, I'm pulling that max surrogate value as right stream, and I'm getting the staging data as left, and I'm doing a custom cross join. Now what this will do is it will basically bring the fields in for both of these sets of records. And we can see that if we just go to data preview and hit refresh. So you see now there's a new field called max surrogate, and it has the value 15. That's the maximum widget key. Now if I go to the next step, this is add surrogate key root. Now this is a special block, and what it does is it starts with a value. You can set any value. I started at 1, and it will numerically add 1 to every single value for each record. So we will have a new field called surrogate key root, and it'll go 1, 2, 3, 4, 5, etc. So if I hit data preview on here, okay, so if I scroll over to the right here, my max surrogate field is 15. My surrogate key root is 1 and then 2. So it adds 1 for each record. So what I'm going to do is I'm creating a widget key by adding these two fields together. That's what I'm going to do in the next step. So you'll see what that'll do is our latest widget key value is 15. So this new one will be 15 plus 1, which is 16. And then this one will be 15 plus 2, which is 17. So by adding to the highest widget key, we make sure we create unique widget keys. So if I go to the next step, that's exactly what I'm doing. I'm pulling in those results, and I'm setting a bunch of fields. I'm setting the start date to the current date, because these are all new inserts, so they're going to have a start date of now. The widget key, as I mentioned, is adding the max surrogate and the surrogate key root together, and I'm just turning it into an integer. Active flag is set to true because these will all be active records, and the end date is set to null because they won't have an end date. So finally, the last step inserts that data into widget dim2, or our destination table. So if I go to data preview and I hit refresh, you see what's going to be inserted into the table. There's going to be two new widget keys, 16 and 17, because remember, the one that already exists in there is 15, so that makes sense. It stores our widget IDs from the original table, 1 and 4. And remember that 1 is actually an update. So it's a new record with the updated values. This has been updated. Cost is now $225. Start date for these values is today, and no end date because it's the active record. It says the active flag. And the inserted one is exactly the same thing. It's the values and it's active. So those are the new active values for those two widgets. Now let's take a look at what the update does. So on to the next row. In this case, we're not getting the data from staging, but we're getting the data from the actual destination. And what we're going to do in the next block after that is we're going to filter it because we only want to take a look at the active records. We want to get all the active records. So if I do a data preview of that, the idea for this is now that we've inserted the new records, we want to update the old records. So we want to get the records that are marked as active but are not part of the set that was just inserted. That's what the next several steps achieve. So you'll see the one that it picks up is widget key 15, existing widget. That's the widget ID number 1 from the original table. It's currently active because we haven't set it as inactive yet. But we've already inserted a record that's the newest record for this one that's active. So now there's 2 that are active for widget ID 1. One we've just inserted and this one. The next step, now that we've filtered so we're only looking at active records, so now what we're doing is we're doing an exists, and what this does is it checks to see if there's records in both the active records we just filtered and in staging that both have the same widget ID. This will essentially get only the records that need to be updated. So what this step does is it filters out the records that have just been entered. So we have active records in the data set that have just been inserted by this insert destination up here. So this filters those out. When we get past this, we have active records that are old records. They're not just newly inserted. Now that we have all those active records that are old and should be marked inactive, that's exactly what we do. So in the next step, we set some columns. We set the active flag to false, and we set its end date because now that record has a start and end range. It ends at the current date. So we set the end to the current date UTC. So if we take a look at the data preview on this one, okay, so you see what it's going to do is it's going to take widget key 15, so this is the existing widget that was already in our destination table, widget ID 1, and it's going to set it to inactive, from active to inactive, and it's going to set its end date. It's also changed its cost and its name. So that's exactly what we want. So the next step is called required for update. I'm just going to skip this one because it's just required to do the step that follows. It doesn't do anything very interesting. On the next step, update, this is going to put the results into our destination table, and it's going to do an update. Okay, so what we're going to do now is we're going to run this and see the results. So on the left, if I go to pipelines and I go to slowly changing DIMS 2, now I created this pipeline, and the only thing I did to add this data flow is I just went to the left under data flows and I dragged the data flow over and put it on the pipeline. When you do that, you can now run that data flow by adding a trigger. So I'm going to add a now trigger. I'm going to go under add trigger and go trigger now. Hit OK. So now it's running, and this is going to take about 5 minutes, so I'm just going to pause and come back. Okay, that's finished. So let's take a look at what has happened in our database table. So if I go back to SQL database, and now I'm going to run and take a look at our destination table. Expand this a little bit. And what you're going to see is that there are now 2 records for widget ID 1 because that's the record that we updated. So it's stored the newer values and also the historical values that we just changed. So this is why we need a widget key, because we have these 2 records with the same widget ID. The first one is the existing widget, and it has a start date and an end date, and its active flag is set to false. So that's now a historical record and no longer the active record. The active record for one is this number 16 widget key. This has been updated and it's the new value, and it has a start date of today and no end date because it's active, and its active flag is set to true. We also inserted a record that didn't previously exist, and that's number 17, and that's widget ID 4. It's a new widget and it's $20.50, and it has today as a start date, and again it's an active record and so has no end date. So what you can do is you can query this table, and you can query for active flag is true, and you can get all the most recent values. You can also query the historical values and do analysis of that. So in conclusion, this demonstrates how to ingest slow changing dimensions and store them with history. In this video, we're going to look at folder structures in a data lake. A data lake folder structure works much like the folder structure in your Windows operating system. with potentially nested folders and documents. There's no one right way to set it up. There are several factors that you need to consider, however, when setting up your folder structure in a data lake. You need to consider business needs. The data needs to be accessible to those who need it. You don't want to end up with data that's not being used in what's commonly referred to as a data swamp. There are security needs that need to be considered. In a data lake, access is typically granted granularly at the folder and document levels, and permissions are typically inherited by subfolders and documents. So how you nest folders and documents is going to make a difference. And you need to consider performance, since many roles with different needs are going to be accessing the data in the data lake. It should be organized to facilitate efficient querying based on the expected usage patterns. What are the benefits to being diligent with your folder structure? One that was previously mentioned was security. Permissions can be set at the folder and document level, but this will be much simpler and therefore less prone to mistakes if the folder structure is conducive to security access patterns. Consider a collection of documents in a data lake that need to be accessed by a group of people with the data analysis role. Now imagine documents are added to this collection daily. If the documents are not all grouped under a common folder, then permissions may have to be assigned dynamically at the document level as documents come in, which can get complicated and error-prone. If they're stored in a common folder, however, then role-based permissions for the data analysis role can be applied to that folder and all documents under it, which is much cleaner. When best practices are followed for folder structure, the structure becomes easier to navigate, making it more usable. Users should not be hindered by the folder structure. If the folder structure is well thought out, it will allow for future extendability. This involves thinking about the likely future uses and the best way to serve those uses with the structure. A good folder structure makes governance practices much easier, from managing metadata, automating quality assurance, and performing functions such as moving data to archive as part of an information lifecycle management policy. Here are some best practices for managing folder structure in a data lake. Make folder and document names human readable. This just makes sense for making the structure more usable. The same goes for other folder structures besides data lake. I once worked with someone who managed folders in the cloud storage system Box by prefixing folders with numbers, which made no sense to anyone but him. It unnecessarily made the system very difficult to use. Try to make operations lives bearable by planning permissions correctly. They should be granular, in that the correct roles can be given permission to what they need and just what they need. But the strategy cannot be so complex that operations are pulling their hair out trying to manage it. For instance, many permissions at the document level are probably not a good idea. Think of data access patterns and try to partition data in such a way that it makes data retrieval efficient along the lines of those patterns. And the files should be organized within the folders. Best practice is to store files of the same schema and format in the same folder. For instance, one folder may contain JSON files with a particular schema because they're ingress data from an HVAC unit. Don't group disparate files. Instead, consider making subfolders based on format type and schema. One overarching strategy you can consider is data lake zones. Data lake zones organize data into areas according to their location in the data pipeline. First, there's the raw zone. This is the data that has just been ingested into the system in its raw state. It hasn't been manipulated in any way. To maintain the integrity of the data pipeline, it's important that this data is not modified outside of the pipeline, so this data should be read-only. Then you have the cleansed zone. This is the data from the raw zone that's had all unnecessary data, such as unnecessary columns, removed. This data then moves on to the curated zones. This is data that has been transformed, so it's meaningful and useful to data scientists. And finally, the laboratory zones represents data being actively used by data scientists. It will be partitioned into folders per group of data scientists who are using it. This table shows some potential details for a folder structure set up in data lake zones. First, the raw zone. This zone typically accepts large amounts of ingress data, so possible volumes for this zone are terabytes per day. A proposed path for this might be to have the project name as the root folder, since organizing by projects makes sense, and then a raw files folder representing the raw zone for the project. And subfolders underneath that organize the data temporally down to the minute, since the data flow is high. Next, there will be less cleansed and curated data than raw data, as data is pared down and the unnecessary data removed. So you may expect gigabytes per day in this zone. The project path can be raw data under the project name, and subfolders might organize the data down to the day, since it will be updated less frequently than raw ingress data. And finally, for the laboratory zones, there may be megabytes of data flowing in per day to be worked on by research groups. The project path can be business data after the project name, then possibly partitioned into research groups below that. The subfolders can organize the data to the granularity of a month, which is a sort of time frame granularity for most projects. In this video, I'm going to show you how to use an external table in Polybase to import data into Synapse Analytics. Now, external tables are not physical tables, but they're mappings to external resources, such as blob storage. Polybase with external tables is one of the fastest ways to import data into Synapse Analytics from an external source. So the Polybase process involves three tables. There's an external table, which is virtual, so it's not a physical table in the database, but only a mapping to an external source, and in this case that's going to be a blob. We'll also use a staging table, which is a physical Synapse Analytics table that accepts the data from the external table or blob. And then finally we'll have a production table, which is a physical table again that accepts data from the staging table. So there's three stages: external table, staging table, production table. Now in our example, we're not doing any transforms of this data. But if we did do transforms, it could happen between the staging and the production tables. So I'm in Microsoft Azure, and I'm just going to go to my resource group that I have set up, and I'm going to get right into Azure Synapse. So you need to have an Azure Synapse instance, a Synapse workspace set up. Now, first thing I'll mention is that you have to have a SQL pool set up as well. So on the left, if you go under SQL pools, you can click New, and you can create a new dedicated SQL pool. Now, I already have one called Synapse 45363 right here. So that's the one we're going to be using. Now, if I go back to my overview, I'm going to scroll down and go to Open Synapse Studio, and I'll click. Okay, and on the left, I'm going to click Data, and this gives us a query view, and then we can run our Polybase from here. So on the left, if I open databases, when you created that SQL pool, it will appear here. Mine is Synapse 45363, new SQL script, empty script. Now the first one I'd run is create master key encryption by password equals, and I would give it some password. So this encryption master key needs to be set once per database. Now I already set it on this one, so I'm not going to run it again. But you would just choose a password and then run this. The next thing that you do is you're going to set up a scoped credential. Now what this is, the credentials to talk to our blob. Our blob is in an external storage account in Azure. So it goes create database scoped credential, and I just give it a name. Mine's called blob credential, but it could be anything. On line 2, I have with identity equals, and this is what you use for blob storage in Azure, shared access signature. And then on line 3, secret equals, and I have to give it the storage account key for the blob. So if I go back to Azure, so I'm going to go to my storage account, which is storage 2426 in my case. So you'll need an Azure storage account set up. And I'm going to go to containers because it's a blob container. And if you don't have a container set up yet, you can hit plus container at the top and create a new container. I already have a container called demo. So I'll go in there. And I also have a CSV loaded. This is the data that we're going to read via Polybase. So if I click on people.csv, it's just a real simple CSV. If I click on edit to the right, you can see that it has two fields, a name and an age. And those are the two fields that our table is going to have as well. And so I have Joe Smith, who's 45, Sally Jones, who's 36, and Timothy Doe, who's 71. So if I just go back to Synapse for a moment, what we need is the storage account key. So if I go back to the overview of the storage account, and I click on Access Keys, and I click Show Keys, and I will copy the first key, and go back to Azure Synapse Analytics, and on line 3, I will paste that storage account and hit Run. So this sets up a credential. The next thing that we're going to do is we're going to create our external data source. So here's the query for that. Create external data source blobs with, and in round brackets on line 4, we have type equals Hadoop. That is the type for blob storage. On line 5, credential equals blob credential. That's that object that we just created. And on line 6, location equals, and we have to fill this out. It has a specific format. WASBS : //, then the name of my blob container, and then and the name of my blob account, and then .blob.core.windows.net. So the name of my container is demo, as I showed you before. So I'll fill that in. And if I just go back to Azure, you'll see the name of my account is storage2426. So I will fill that in as the account. I'll click Run. So that creates my data source. If we look at external resources right now, and look at external data sources, we'll see my data source. And you'll see on line 1, it was called blobs. So there it is, it's blobs. So that connects me to my external blob storage. The next step is to create an external file format. Now what this does is it tells Polybase what the format of the blob that I'm about to read. So we'll just call that CSV format. And I'll just step you through the query here. Create external file format CSV format with round brackets on line 4, format _ type equals delimited text. That is the type for CSV. On line 5, format _ options. And then round brackets on line 7, field _ terminator. In our CSV, the fields are terminated by a comma. And on line 8, string _ delimiter. And it is actually the double quote, hex 22. And on line 9, first _ row equals 2. That tells it to start on the second row because the first row is the names of the fields. So if we run this, it creates that format that we can reference. And on the left, you see there's a folder under the database called external file formats. And we've now created CSV format. So our next step, what we're going to do is we're going to create 3 schema. Schema partitions our database. So we're going to have one table in each of these schema. The first schema on line 1, create schema ext, so that's our external schema. We're going to put our external table in that. Line 3, that's the schema for our staging table. And on line 5, create schema prd, that's the schema for our production table. So I've run that. So now, when I look under schemas to the left under the database, I should see ext, prd, and stg. There they are. So the next thing we're going to do is create our external table. So here's the query for that. Create external table ext.people. So ext is our schema. Round brackets, and it has 2 fields. On line 3, we have a name field that's a string. And on line 4, we have an age field that's an integer. Starting on line 6, we define the data source for this external table. You need to remember that an external table is not the same as a physical table in Synapse Analytics. The definition of it is stored in Synapse Analytics, but it actually points to an external reference, and that's where it gets its data. So if starting on line 6 with round bracket location equals, and I give it / and the name of the CSV file. And then on line 7, data _ source equals blobs. Remember that that's our external data source. Okay, I realize one thing that we're missing is the file format, so we also have to specify that. On line 8, So we have the data source equals blobs, file format equals CSV format. That's the format that we created. So I hit run, and that's now created the external table. If I go to the left and I open up external tables, I see my ext.people. So what we've done is we've created an external table now that is referenced to that CSV and is going to read the data out of it using this CSV format. So the next step is to try to query that. So select star from ext.people, we'll run that. And indeed, what we have is the 3 records that are in our CSV blob. Joe Smith is 45, Sally Jones is 36, Timothy Doe is 71. Now again, it's important to realize that this data is not currently stored in Synapse Analytics. It's stored in that blob, and we are only reading it using an external table. So the next thing we're going to do is we need to create a physical table. So we're going to create a staging table. Create table stg.people as, and we're going to select star from ext.people. So it's going to copy everything from the blob referenced by that external table into this physical table that it's going to create. And another thing that we're missing here is a with statement. So when you do this, this is actually a parallel process. So when you create this table and you reference a select star from the external table, you have to add a with in between on line 2 here. With round brackets distribution equals, and you have to give it a parallel distribution method. So we're going to use round robin. So I'll hit run, and that's complete. So now on the left, if we go to tables, we see our staging table, stg.people. And if we choose to see everything in the staging table, run the select star, we see our data now. There's our 3 fields. So this data is now physically in Synapse Analytics. So using a Polybase external table, we've brought this into Synapse Analytics in a staging table. Now, normally the reason you have a staging table is if you want to do some transforms on the data when it goes from staging to production, or if you want to do some test of the data, you have it in staging before it goes to production. So now we're going to create a production table. So I'll create table prd.people, and it's got the name and age. I'll run that. And now if I refresh the tables on the left-hand side, I see I now have a staging people and a production people table. And all that's left to do is simply move that data from staging to production. Now this is our trivial move, which doesn't do any transforms or anything. It inserts into prod.people, select star from staging.people. So it just moves everything. And it's complete. And now if I look at my production people table and I do a select star, there's all my data. So in conclusion, with some TSQL statements, you can use Polybase to import data from a blob storage container into Synapse Analytics. External tables can be used for sourcing data from Hadoop and Azure Data Lake as well. In this video, we're going to discuss accelerating queries. In Azure, this is a feature that can be used by clients when they're querying Data Lake. And it works with 2 concepts. Predicates are expressions that are evaluated to either true or false, and records will only be returned if the predicates evaluate to true. This gives a developer control to filter queries based on business logic. The other is column projections, which is filtering out unwanted columns in the resulting records, only returning the columns of interest. In the past, Data Lake data has returned all columns of data when queried, and the client might filter the result on the client side, which is inefficient. These operations are made efficient by Data Lake, since they're performed by the Data Lake engine, and this serves to accelerate the queries run by the client. So let's look at the process flow for query acceleration. First, the client submits the request for data, and this request contains any required predicates and column projections. In Azure, this is done as a SQL query select statement. Predicates are represented as SQL row filter statements, such as where and in, while column projections are specified in the column specification of the select statement. When Azure Data Lake retrieves the request, the query acceleration engine parses the SQL and distributes query jobs accordingly. This is the query acceleration step of the flow, as this is where the retrieval of the data is done as efficiently as possible. The data is then retrieved by data lake and returned to the client. The client can now consume the data without further filtering, because all filtering has been done at the data lake server. A few use cases for data acceleration are distributed analytics frameworks like Apache Spark and Hive, which have recently become more integrated with query acceleration for efficiency, and any data processing applications that require processing efficiency and speed. Now, there are some limitations to query acceleration that should be noted. Query acceleration only targets a single file or blob. So say you have a CSV file that contains many rows. You can query for specific data in that file using a single query, but you cannot use a single accelerated query to return the contents from several files. This means that you cannot filter using complex structures that involve multiple files or blobs, such as joins and group bys. So in practice, you may want to consider query acceleration when designing your data queries. While joins and group bys are sometimes required, you should also consider alternatives that avoid such operations so that your queries can take advantage of query acceleration. In the long run, this may simplify your data organization as well as your data queries. Some important query acceleration features are support for CSV and JSON, which are two of the most popular formats for data in Data Lake. These are also popular raw data formats for ingress data, meaning that query acceleration can be used to query raw data coming into Data Lake without need for transformations. This equates to faster queries. Data Lake Storage supports query acceleration. Data Lake Storage is often used to store data as it moves through the data pipeline, and it's also used as a main data source for data analysis performed by end users such as data scientists. So this means that query acceleration will be beneficial to end users of the data. It's also supported by regular blob storage, which is often used as a landing technology for incoming data, meaning that processes can efficiently query raw incoming data with query acceleration. So in conclusion, query acceleration is another step toward making data access more accessible and efficient. It simplifies the logic of clients, such as data scientists or services that perform analysis, because it simplifies the filter logic that needs to be put in the client code or script. It can also simplify data transforms in the data pipeline, because where transforms might have previously filtered the incoming raw data, now the query acceleration feature can manage it at query time. So in this course, we've examined how to define mature logical data structures for big data implementations. We did this by exploring key concepts for maturing data lake storage structures, temporal database tables and how to manage them, slowly changing dimensions and building a type 1 and type 2 changing dimension, effective logical file and folder structures, using Polybase to build external tables, and accelerating queries against data in Azure Data Lake Storage Gen 2. In our next course, we'll move on to examine how to design and implement the serving layer in a data lake deployment.